Question number 12. A. Two insulated charged copper spheres A and B have their centers separated by a distance of 50 cm. What is the mutual force of electrostatic repulsion if the charge on each is 6.5 into 10 raised to minus 7 coulomb? The radii of A and B are negligible compared to the distance of separation. Consider two copper spheres A and B. They are separated by distance r is equal to 50 cm. The charges on both the spheres are equal. Given QA and QB is equal to 6.5 into 10 raised to minus 7 coulomb. R, that is 50 cm. This is equal to 0.5 meter. Now we have to find the force of repulsion between these two copper spheres. According to Coulomb's law, F is equal to 1 by 4 pi epsilon 0 QA, that is charge at A, into QB, that is charge at B, divided by distance between these two spheres, that is r square. Now substitute the values. This is equal to 1 by 4 pi epsilon 0, that is 9 into 10 raised to 9 into QA and QB, that is 6.5 into 10 raised to minus 7 whole square, all divided by r, that is 0.5 square. This is equal to 1.52 into 10 raised to minus 2 Newton. Therefore, the force of repulsion between these two spheres, F is equal to 1.52 into 10 raised to minus 2 Newton. Question B. What is the force of repulsion if each sphere is charged double the above amount and the distance between them is halved? Now the charges on both the spheres are double the above amount. Therefore, the new charges on copper spheres are QA prime is equal to 2QA and QB prime is equal to 2QB. The distance between these two spheres is halved. That is, r prime is equal to r by 2. Now what is QA and QB? QA is equal to 6.5 into 10 raised to minus 7 coulomb. This is equal to QB. R is equal to 50 centimeter. This is equal to 0.5 meter. Now substitute the values. This is equal to 2 into 6.5 into 10 raised to minus 7. This is equal to 1.3 into 10 raised to minus 6 coulomb. Similarly, QB prime is equal to 2 QB. This is equal to Therefore, the new charges on the copper spheres are 1.3 into 10 raised to minus 6 coulomb and the distance between them r prime is equal to 0.25 meter. According to Coulomb's law, the new force of repulsion between these two copper spheres F prime is equal to 1 by 4 pi epsilon 0 QV prime QB prime by r prime square. Now substitute the values. Equal to 0.243 Newton. Therefore, the new force of repulsion between these two copper spheres A and B is F prime is equal to 0.243 Newton. Question number 13. Suppose the spheres A and B in exercise 12 have identical size. A third sphere of the same size but uncharged is brought in contact with the first, then brought in contact with the second, and finally removed from both. What is the new force of repulsion between A and B? From the previous question, we know that the charges on two spheres Q is equal to 6.5 into 10 raised to minus 7 coulomb and the distance between these two is r equal to 0.5 meter. Now, a third sphere, let it be C, of same size but uncharged is brought in contact with sphere A. When two spheres with different charges brought in contact with each other, what happened here is their charges will share equally. That is, A is having a charge Q and C is having a charge 0. So they will share their charges equally. So Q plus 0 by 2, this is equal to Q by 2. Therefore, the charges on each of the sphere A and C is now become Q by 2. Initially, the charges on A is Q and C is 0. When they touch each other, their charges share equally. Now the new charges become Q by 2. Now, sphere C with charge Q by 2 is touched with sphere B with charge Q. Here also, the charges will share equally. That is, C having a charge Q by 2 plus B having a charge Q, they share their charges equally. Therefore, the total charge on the system will divide into 2 equal half. This is equal to 3Q by 4. Therefore, the charges on each of the sphere C and B now becomes 3Q by 4. Finally, C is removed from both. Now the new charges on A and B is Q by 2 and 3Q by 4. Now we have to find the force of repulsion between these two spheres. According to Coulomb's law, the force of repulsion between these two spheres F is equal to 1 by 4 pi epsilon 0 QA QB by R square. Now what is QA and QB? QA is Q by 2 and QB, that is charge on B, is 3Q by 4. Now substitute the values. This is equal to 1 by 4 pi epsilon 0, that is 9 into 10 raised to 9 into QA, that is Q by 2 into QB, that is 3Q by 4, all divided by R, that is 0.5. So 0.5 whole square. This is equal to 9 into 10 raised to 9 into Q into Q, Q square. Now what is Q? That is 6.5 into 10 raised to minus 7 coulomb. 3 into 6.5 into 10 raised to minus 7 whole square. All divided by 2 into 4, 8. 8 into 0.5 whole square. This is equal to Therefore, the new force of repulsion between these two spheres F is equal to 5.703 into 10 raised to minus 3 Newton. Question number 14. Figure 1.33 shows tracks of 3 charged particles in a uniform electrostatic field. Give the signs of the 3 charges. Which particle has the highest charge to mass ratio? We know that same charges repel each other and unlike charges attract each other. Particle 1 and 2, they move towards the positive plate and repel from this negatively charged plate. Hence 1 and 2 are negatively charged particles. Similarly, particle 3, it attracted towards this negatively charged plate. Hence, it is a positively charged particle. Which particle has the highest charge to mass ratio? Charge to mass ratio depends upon the vertical displacement, that is, how much the particle is deviated from its original path. The relationship between the vertical displacement and charge to mass ratio is y is equal to QEL square by 2m Vx square. We will prove this relation in additional exercise question number 33. Therefore, charge to mass ratio Q by m is directly proportional to the vertical displacement y. So, which particle has the highest vertical displacement, that is highest amount of deflection? That particle has the highest Q by M ratio. So when you carefully look at the figure, you can see that particle 3 is deviated more when compared to other two particles. Hence, it has the highest charge to mass ratio. Question number 15. Consider a uniform electric field E equal to 3 into 10 raised to 3 I cap Newton per coulomb. A. What is the flux of this field through a square of 10 cm on a side whose plane is parallel to the YZ plane? Consider a square of side 10 cm. Let x, y, z be the coordinate axis. This plane is parallel to YZ plane. The area vector is normal to the surface so that it is acting along x-axis. Given E is equal to 3 into 10 raised to 3 I cap Newton per coulomb, where I cap is the unit vector along x-axis. Therefore, electric field is acting along x direction. E is acting along x-axis. Now we have to find the flux through this square. Flux through the square phi is equal to EA cos theta. Now substitute the values. Now what is magnitude of E? This is 3 into 10 raised to 3 Newton per coulomb. Now what is area? Area of the square is A square, where A is 10 cm. So this is equal to 10 square, that is 100 cm square, or 0.01 meter square. Area of the square is equal to 0.01 meter square. Now theta, that is the angle between E and A. Since electric field and area vector both are acting along x-axis, therefore the angle between E and A is 0 degree. Now substitute these values. Flux phi is equal to E, that is 3 into 10 raised to 3 Newton per coulomb, into area of the square, that is 0.01 meter square, into cos 0 degree. This is equal to 30 Newton meter square per coulomb. Therefore, flux through the square is equal to 30 Newton meter square per coulomb. Question B. What is the flux through the same square if the normal to its plane makes a 60 degree angle with the x-axis? Here the plane is inclined so that the area vector which is normal to the surface is making an angle 60 degree with the x-axis. Therefore, flux through the square phi is equal to EA cos theta. Now substitute the values. E, that is 3 into 10 raised to 3 into area. Area of the square is A square, that is 0.01 meter square. So this is 0.01 meter square into cos. What is the angle between E and A? Since this electric field is acting along x-axis, so angle between E and A is 60 degree. This is cos 60 degree. This is equal to 30 into cos 60, that is half. This is equal to 15 Newton meter square per coulomb. Therefore, the flux through this inclined plane is equal to 15 Newton meter square per coulomb. Question number 16. What is the net flux of the uniform electric field of exercise 15 through a cube of side 20 cm oriented so that its faces are parallel to the coordinate planes? Consider a cube with sides 20 cm. Let x, y, z be the coordinate axis. Here, all the faces of the cubes are parallel to the coordinate planes. The left and right faces are parallel to YZ plane, and the top and bottom faces are parallel to XY plane, and the front and back faces are parallel to XZ plane. Now we have to find the net flux passes through this cube. From exercise 15, we know that the the electric field is acting along x-axis, that is E is equal to 3 into 10 raised to 3 I cap Newton per Coulomb, where I cap is the unit vector along x direction. Therefore, electric field is acting along x-axis. Consider the top and bottom faces. The area vector is normal to the faces and the electric field is acting along x-axis. Therefore, the angle between A and E is 90 degree. Now, what is flex? Phi is equal to EA cos theta. Here, theta is 90 degree. Therefore, phi is equal to EA cos 90 degree and cos 90 is 0. Therefore, there is no flex passes through the top and bottom faces. Similarly, for the front and back faces, the area vector and electric field is acting perpendicular to each other. Therefore, no flex passes through these two faces. Now consider the left and right faces of the cube. These two faces are perpendicular to electric field. Therefore, the area vector is acting along the field so that the flex will pass through these two faces. Through this left face, the flex will enters into the cube and it leaves out through the right face. Since E is same for the left and right faces because this is a uniform electric field. Therefore, phi in is equal to phi out. Now, what is the flex through this left face? That is phi in. Phi in is equal to EA cos theta. Since the electric field is acting along this direction and area vector is acting along this direction, therefore, the angle between these two is 180 degree. Now, cos 180 is minus 1. So, this is equal to minus EA. Similarly, the flex that leaves out through the right face is equal to phi out is equal to EA cos 0 degree because electric field and area vector both are acting along x direction. Therefore, cos 0 degree, this is equal to EA. Therefore, the flex that enters the cube is minus EA and that leaves out through the right face is EA. Therefore, the net flex passes through the cube is equal to phi in plus phi out. This is equal to phi in, that is minus EA plus EA. This is equal to 0. Therefore, the net flex passes through the cube is equal to 0. Or we can say the number of field lines that is entering the cube is equal to number of field lines that is passing out of the cube. Phi in is equal to phi out. That is, whatever flex entering the cube will leave out of the cube. As a result, the net flex through the cube is equal to 0. Question number 17. Careful measurement of the electric field at the surface of a black box indicates that the net outward flex through the surface of the box is 8 into 10 raised to 3 Newton meter square per Coulomb. A. What is the net charge inside the box? The net flex through the surface phi is equal to Q by epsilon 0. Given the flex through the surface of the box is 8 into 10 raised to 3 Newton meter square per Coulomb. Now we have to find the net charge inside the box. From this, net charge Q is equal to epsilon 0 phi. Now substitute the values. This is equal to 7.08 into 10 raised to minus 8 Coulomb, or this can be written as 0.07 microcoulomb. Therefore, the net charge inside the box is equal to 0.07 microcoulomb. Question number B. If the net outward flex through the surface of the box was 0, could you conclude that there were no charges inside the box? Y or Y naught. Net outward flux through the surface of the box was 0 means phi out is equal to 0. Now what is phi? This is equal to Q by epsilon 0. Since epsilon 0 is a constant, therefore Q is equal to 0. Now what is Q? This is the net charge enclosed by the surface. Therefore, Q equal to 0 means a system may contain no charge. There is another possibility that a system may contain equal number of positive and negative charge. Suppose if a system contains plus phi charge and minus phi charge, therefore the sum of these two charges is equal to 0. That is, Q is equal to 0. So this is the net charge enclosed by the surface. So there are two possibilities. Therefore, even if the flux is 0, we cannot conclude that the net charge inside the box is 0. There is another possibility that a system may contain equal number of positive and negative charge. Question number 18. A point charge plus 10 microcoulomb is a distance 5 cm directly above the center of a square of side 10 cm as shown in figure. What is the magnitude of the electric flux through the square? Hint. Think of the square as one face of a cube with edge 10 cm. We are solving this problem by constructing a cube of sides 10 cm so that the charge is exactly at the center of this cube. This is one of its face. The flux passes through a closed surface is given by Gauss Law. That is, phi is equal to Q by epsilon 0. Here, the cube is the Gaussian surface and the charge is enclosed by the cube. Since the charge is exactly at the center of this cube, thus the flux originating is symmetrically passes through all the 6 faces of the cube. Therefore, this is the total flux passes through the cube and this is equal to Q by epsilon 0. Now we have to find the flux through the square, that is through this shaded face. Through this shaded face. Since a cube has 6 faces, so flux through one face is equal to phi is equal to 1 by 6 of Q by epsilon 0. Now what is Q? It is 10 microcoulomb. So this is equal to 1 by 6 into 10 microcoulomb. So 10 into 10 raised to minus 6 coulomb divided by epsilon 0, that is 8.854 into 10 raised to minus 12. This is equal to 1.88 into 10 raised to 5 Newton meter square per coulomb. Therefore, the flux through the square is equal to 1.88 into 10 raised to 5 Newton meter square per coulomb. Question number 19. A point charge of 2 microcoulomb is at the center of a cubic Gaussian surface 9 cm on edge. What is the net electric flux through the surface? Net electric flux phi is equal to Q by epsilon 0. Given Q is equal to 2 microcoulomb, that is 2 into 10 raised to minus 6 coulomb. This is equal to therefore, the net flux through the surface is equal to 2.26 into 10 raised to 5 Newton meter square per coulomb. Question number 20. A point charge causes an electric flux of minus 1 into 10 raised to 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 cm radius centered on the charge. A. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? We know that electric flux passes through a surface is equal to Q by epsilon 0, where epsilon 0 is a constant. So, flux passes through a surface is only depends upon the net charge enclosed by the surface, and it does not depends upon the size of the body. So, if the Gaussian surface is doubled, then the flux passes through the surface remains same. Now, what is flux? Phi is equal to minus 1 into 10 raised to 3 Newton meter square per coulomb. Therefore, even if the size of the Gaussian surface is double, the flux passes through the surface remains same. That is, phi is equal to minus 1 into 10 raised to 3 Newton meter square per coulomb. Question B. What is the value of point charge? Flux through the surface is equal to Q by epsilon 0. From this, Q is equal to epsilon 0 phi. Now substitute the values. 8.854 into 10 raised to minus 12 into 5, that is minus 1 into 10 raised to 3 Newton meter square per coulomb. This is equal to minus 8.854 into 10 raised to minus 9 coulomb, or this is equal to minus 8.854 nano coulomb. Therefore, the value of the point charge Q is equal to minus 8.854 nano coulomb. Question number 21. A conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is 1.5 into 10 raised to 3 Newton per coulomb and points radially inward, what is the net charge on the sphere? We know that the electric field intensity at a distance d from the center of the sphere is E equal to 1 by 4 pi epsilon 0 Q by d square. Electric field is given, that is E is equal to 1.5 into 10 raised to 3 Newton per coulomb. Now we have to find the net charge on the sphere. From this, Q is equal to 4 pi epsilon 0 d square E. Now substitute the values. This is equal to 4 into 3.14 into 8.854 into 10 raised to minus 12 into, what is d? This 20 centimeter. So 20 into 10 raised to minus 2 whole square into E, that is 1.5 into 10 raised to 3. Therefore, net charge on the sphere Q is equal to 6.67 into 10 raised to minus 9 coulomb, or this can be written as 6.67 nano coulomb. Since the electric field is acting radially inwards, so what kind of charge is this? This is a negative charge. For a negative charge, the electric field is acting towards the charge. Therefore, the charge on the sphere is minus 6.67 nano coulomb, because this is a negative charge. Question number 22. A uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter square. A. Find the charge on the sphere. Consider a conducting sphere with radius r equal to 1.2 meter. Given the surface charge density sigma equal to 80 microcoulomb per meter square. This is equal to 80 into 10 raised to minus 6 coulomb per meter square. Now we have to find the charge on the sphere. Now what is sigma? It is the amount of electric charge that is present on the surface of the given area. That is, sigma is equal to Q by A. From this, Q is equal to, that is, charge on the sphere is equal to surface charge density into area of the sphere. Now what is area of the sphere? That is 4 pi r square. Q is equal to sigma, that is 80 into 10 raised to minus 6 into area, that is 18.0864. This is equal to 1.447 into 10 raised to minus 3 coulomb. Therefore, charge on the surface of the sphere Q is equal to 1.447 into 10 raised to minus 3 coulomb. Question number B. What is the total electric flux leaving the surface of the sphere? Total flux leaving the surface of the sphere phi is equal to Q by epsilon 0. This is equal to, what is Q? It is 1.447 into 10 raised to minus 3 coulomb divided by epsilon 0. It is 8.854 into 10 raised to minus 12. This is equal to 1.63 into 10 raised to 8 Newton meter square per coulomb. Therefore, the total flux leaving the surface of the sphere is 1.63 into 10 raised to 8 Newton meter square per coulomb. Question number 23. An infinite line charge produces a field of 9 into 10 raised to 4 Newton per coulomb at a distance of 2 cm. Calculate the linear charge density. Consider an infinite line charge. Let P be a point at a distance r equal to 2 cm. We know that electric field at P produced by an infinite line charge at a distance r is given by E is equal to lambda by 2 pi epsilon 0 r, where lambda is the linear charge density. Given E is equal to 9 into 10 raised to 4 Newton per coulomb, r is equal to 2 cm. This is equal to 0.02 meter. Therefore, linear charge density lambda is equal to 2 pi epsilon 0 r E. Now substitute the values. This is equal to 2 into 3.14 into 8.854 into 10 raised to minus 12 into r, that is 0.02 into E, that is 9 into 10 raised to 4. This is equal to 10.0085 into 10 raised to minus 8, or this can be written as 10 raised to minus 7 coulomb per meter. Therefore, linear charge density for a infinite line charge lambda is equal to 10 raised to minus 7 coulomb per meter. Question number 24. Two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite signs and of magnitude 17 into 10 raised to minus 22 coulomb per meter square. What is E in the outer region of the first plate, B in the outer region of the second plate, and C between the plates? Consider two thin parallel plates A and B. Let sigma be the surface charge densities. Given they are of opposite signs. That means one plate is positively charged, another one is negatively charged. Now we have to find the electric field in the outer region of first plate and the second plate, and also between the plates. We know that for a positive charge, electric field lines are directed away from the charge. So here the field lines are directed away from the positive plate. Similarly, for a negatively charged plate, the field lines are directed towards the charge, that is towards the plate. So here the blue line indicates the field lines are directed away from the charge, and this red line indicates the field lines are towards the plate. Consider a point P outside of plate A. The electric field at P due to this positive plate act along this direction, that is away from the charge. The electric field at the point P due to this negative plate act along this direction, that is towards the charge. So this is E plus, that is electric field due to this positive charge, and this is E minus, that is electric field due to negative charge. Both are acting opposite direction. Therefore, the net electric field at P is equal to E plus minus E minus. because E plus and E minus are acting opposite direction. Therefore, E plus minus E minus. Now, what is E plus and E minus? We know that for a thin plane sheet, electric field is given by E is equal to sigma by 2 epsilon 0. So, this is equal to E plus, that is sigma by 2 epsilon 0, minus E minus, that is sigma by 2 epsilon 0. Therefore, the net electric field at P is equal to 0. Now consider a point outside of plate B, let it be Q. The electric field due to this positive plate acts along this direction, and for a negative plate acts along this direction. So, this is the direction of E plus and this is the direction of E minus. Both are acting opposite direction. Therefore, the net electric field at Q, that is E at Q, is equal to E plus minus E minus, because E plus and E minus are acting opposite direction. This is equal to sigma by 2 epsilon 0 minus sigma by 2 epsilon 0. This is equal to 0. Therefore, the net electric field outside plate B is equal to 0. Now consider a point O between the plates. The electric field due to a positive charge is act along this direction, that is away from the charge. So E plus is acting along this direction, and the electric field due to a negative charge will also act along this direction, that is towards the charge. So this is the direction of E minus. Both are acting same direction. Therefore, the electric field at O due to positive and negative plates are act along same direction. Therefore, electric field at O is equal to E plus E minus, because E plus and E minus both are acting along same direction. Therefore, resultant electric field at O is equal to E plus E minus. This is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. This is equal to sigma by epsilon 0. Therefore, the electric field between the plates is equal to sigma by epsilon 0. This is a very important relation. For a thin parallel plates, there is no electric field outside the plates. Only between the plates there is electric field, and that is equal to sigma by epsilon 0. Therefore, electric field at O is equal to sigma by epsilon 0. Now substitute the value. E is equal to, what is sigma? That is 17 into 10 raised to minus 22 coulomb per meter square, all divided by epsilon 0, that is 8.854 into 10 raised to minus 12. This is equal to 1.92 into 10 raised to minus 10 Newton per coulomb. Therefore, electric field between the plates is equal to 1.92 into 10 raised to minus 10 Newton per coulomb. Therefore, for a thin parallel plates with opposite charges, electric field equal to 0 outside the plates, and between the plates E is equal to sigma by epsilon 0.